In our Milky Way galaxy alone, there are more than 200 billion stars, and many of them are billions of years older than our own Sun. Orbiting these stars are trillions of planets, a number so vast it truly challenges the imagination. By the laws of probability, this sheer cosmic abundance suggests that life should not be a rarity, and intelligence should not be a unique phenomenon. The galaxy ought to be humming with signals, glowing with the waste heat from colossal machines, and teeming with civilizations that had a head start of millions, if not billions, of years. And yet, when we point our instruments to the sky and listen, we are met with an unnerving quiet. There are no visitors, no unmistakable signs of cosmic engineering, just a profound and unsettling silence. Tonight, we will explore 30 of the most compelling and sometimes terrifying ideas science has conceived to explain this cosmic solitude. If you're ready to delve into this mystery, be sure to like this video as we begin our journey. This deep scientific puzzle began not in an observatory, but during a simple, everyday moment. The year was 1950, when a small group of physicists at the Los Alamos National Laboratory gathered for lunch. Among them was Enrico Fermi, one of the principal architects of the nuclear age. Their conversation meandered from hard science to science fiction, touching upon flying saucers and the possibility of life beyond Earth. Then, amidst the casual chatter, Fermi posed a question so simple, yet so powerful, it seemed to cut through the room's noise. Where is everybody? He wasn't asking about his colleagues. He was asking about other civilizations. If the universe is so immense, ancient, and generously filled with stars and planets, then intelligent life should logically be common. Even if it were an exceptionally rare event, occurring on just one in a million planets, that would still imply thousands, or perhaps millions, of distinct civilizations within our galaxy. It was a question that highlighted a stark contradiction, one that continues to haunt us. To truly appreciate why this silence is so disturbing, we must consider the vastness of cosmic time. The Milky Way galaxy is approximately 13 billion years old, while our Sun only formed about 4.6 billion years ago. This means the galaxy had nearly 9 billion years to produce stars and planets before Earth even came into being. It is a staggering thought. Evolution was given a 9 billion year head start elsewhere. One can only wonder what could emerge from such an immense span of time. By comparison, human civilization is barely a whisper in the cosmic narrative. Our agricultural practices began only around 10,000 years ago. Industrial technology is a recent development of just 200 years. And radio communication, our first real attempt to send our voice into the cosmos, has existed for little more than a century. In the grand scheme of the universe, we are infants who have only just learned how to make noise. Now, consider a civilization that emerged just 1% earlier in the galaxy's history than our own. This seemingly small difference would grant them an additional 100 million years of development. To put that into perspective, reflect on how far humanity has progressed in only the last 100 years, from fragile biplanes to robotic explorers traversing the surface of Mars, from candlelight to the dawn of quantum computers. If one were to extend that curve of progress across 100 million years, the result would be a civilization with capabilities almost incomprehensible to us. A society that ancient would not merely explore its corner of the galaxy, it could possess the power to reshape it entirely. This potential for exponential growth is a key part of the puzzle. This is where the paradox becomes especially sharp. While the laws of physics make interstellar travel incredibly difficult, they do not forbid it. A civilization could dispatch self-replicating probes to nearby star systems, even at modest speeds representing a fraction of the speed of light. Upon arrival, each probe could use local raw materials to construct copies of itself, which would then be sent outward to the next set of stars. This process, described mathematically decades ago, would grow exponentially, spreading from one star system to the next, like seeds on the wind. Calculations suggest that even with relatively slow spacecraft, a single civilization could explore or colonize the entire galaxy within a time frame of 1 to 10 million years. While that sounds like an eternity, it is a mere blip when compared to the galaxy's 1-3 billion year lifespan. That entire window of expansion could fit into the galaxy's history thousands of times over. This mathematical certainty leads to a powerful conclusion. If even one civilization had begun to spread millions of years ago, its presence should be obvious and ubiquitous by now. We are not talking about subtle or hidden signs. We mean evidence on a galactic scale. We should be able to detect enormous structures harvesting starlight, or see artificial patterns in the arrangements of planetary systems. Our infrared surveys should pick up the glowing waste heat from advanced technology, and we might even find their probes drifting through our own solar system. At the very least, we should hear the faint, echoing whispers of their signals crossing the interstellar void. Instead, when we look out, we see natural processes unfolding precisely as our understanding of physics predicts. Stars burn, galaxies spin, and planets orbit, but nothing appears engineered. Nothing announces the presence of intelligence on a galactic scale. The contradiction is so stark it feels almost mathematical. In 1961, astronomer Frank Drake attempted to formalize this problem with a simple but elegant tool now known as the Drake equation. This equation breaks the overarching question, how many civilizations are out there, into a series of more specific factors. It asks us to consider the rate at which stars form each year, how many of those stars have planets, and what fraction of those planets could potentially support life. From there, it moves to the probability of life actually arising, of that life evolving intelligence, and of that intelligence developing detectable technology. Finally, and perhaps most crucially, it asks how long such technological civilizations tend to last. It is a framework for organizing our own ignorance. In the decades since, we have made enormous progress on some of these variables. Thanks to missions like the Kepler Space Telescope, we now understand that planets are not the exception but the rule. Nearly every star in the night sky hosts at least one planet, and many host several. Our galaxy likely contains trillions of worlds, with billions potentially situated in what astronomers call the habitable zone, the orbital region around a star, where conditions might allow for liquid water to exist on a planet's surface. The raw ingredients for life appear to be abundant. And yet, the final term in Drake's equation, the average lifetime of a technological civilization, remains a complete mystery. This single variable has the power to change everything. If civilizations typically last for millions of years, the galaxy should be crowded. If they last for only a few centuries before falling silent, the galaxy could be a vast cosmic graveyard filled with the ghosts of civilizations past. Still, even if we assume that civilizations are exceptionally rare, arising only once every million years, the numbers stubbornly refuse to align with the silence we observe. The galaxy has had an abundance of time and opportunity. The fundamental building blocks, chemistry, water, and heavy elements forged in the hearts of ancient stars have been available for eons. There has been no shortage of chances for life to take hold and for intelligence to emerge. A third possibility is that some unknown factor prevents intelligent species from surviving long enough to become interstellar. Before exploring potential solutions, however, it is essential to grasp the full scale of the paradox. This is not a mystery rooted in abstract speculation, but one firmly grounded in simple arithmetic. When one calculates the number of stars in our galaxy, multiplies it by the fraction likely to have planets, then by the fraction where life might emerge, and finally by the fraction where intelligence could evolve, the resulting number of civilizations should be far greater than zero, even with the most conservative estimates. Yet, zero is precisely what we observe. The SETI Institute has found no confirmed extraterrestrial signals. Infrared surveys have revealed no verifiable megastructures. Our own solar system has yielded no alien artifacts, not even ambiguous ruins on the Moon or Mars. We are confronted with a sky that appears as if no one else has ever bothered to ask the same question we are asking now. Where is everybody? The very existence of this question is the problem itself. In a cosmos as ancient and vast as ours, pervasive silence should be the anomaly, while the presence of others should be the baseline expectation. And yet, we find ourselves on a small, rocky world orbiting an unremarkable star, tucked away in the suburbs of a spiral galaxy, listening only to cosmic static. The paradox doesn't definitively prove we are alone. What it does prove is that something in our fundamental assumptions about the universe must be deeply flawed. Perhaps life is exponentially rarer than we imagine, or intelligence is a trait that almost never endures. It could be that advanced civilizations behave in ways we cannot predict, or that we have fundamentally misunderstood what it means to be visible on a cosmic scale. We will investigate each of these possibilities. But first, it is crucial to let the weight of the initial contradiction settle in. The Milky Way has had billions of years and billions of opportunities to produce cosmic company. It had sufficient time for entire empires to rise and fall long before the Earth had even cooled. And still, the cosmic ocean appears profoundly dark and empty. The answer must lie somewhere in the chasm between the staggering probabilities and the deafening silence. To truly appreciate why this silence feels so unnatural, we must stretch our perception of time to its breaking point. The Milky Way galaxy is approximately 13 billion years old, while our own sun is a relative newcomer at about 4.6 billion years old. This means that when Earth first coalesced from a disk of dust and gas, the galaxy was already ancient. Entire generations of stars had already completed their life cycles, living and dying long before our planet even came into being. The heavy elements essential for life, the carbon, oxygen, and iron that constitute our bodies, were forged inside these earlier stars and then scattered throughout space by powerful supernova explosions. This history casts us as latecomers, arriving on a stage that has been set for eons. It raises a critical question. If the necessary ingredients and time were available for so long, why do we appear to be the first to arrive at the party? One way to visualize this immense timeline is to compress the galaxy's entire history into a single calendar year. If the Milky Way formed on January 1st, our sun wouldn't ignite until early September. Shortly thereafter, the Earth would cool, its oceans would form, and the first simple life would emerge. The story of complexity, however, unfolds much later. Complex life doesn't appear until the middle of December. The dinosaurs, which dominated our world for so long, would first walk the Earth on Christmas Day, December 25th, only to vanish on December 30th. In this cosmic calendar, the entirety of recorded human history, every kingdom, every discovery, every revolution occupies only the final few seconds before midnight on New Year's Eve. Our slice of existence is almost immeasurably thin. This perspective forces us to reconsider what, or when, we are actually searching for. When we imagine searching for alien civilizations, we often picture them as our contemporaries, peers looking back at us from neighboring star systems. The deeper reality, however, is that time itself represents a distance as vast and formidable as space. A civilization that emerged 500 million years ago would not just be far away in light years, it would be separated from us by entire geological epochs, and epochs have a way of erasing almost everything. Here on Earth, geological processes continuously recycle the planet's surface. Mountains are pushed up and worn down, oceans open and close over millions of years. The continents themselves drift like colossal rafts on a sea of molten rock. In just a few 100 million years, the vast majority of a civilization's physical evidence would be ground into dust. Cities would be subducted into the mantle, roads would disappear, and even our most enduring monuments would crumble into unrecognizable layers of sediment. Now, imagine that process scaled over billions of years. If an intelligent species had evolved on Earth 2 billion years ago, it is highly probable that no discernible trace would remain today, no fossilized skyscrapers, no derelict satellites in orbit. Everything would have been consumed by tectonics and time. This realization fundamentally changes how we should picture the galaxy. We tend to see it as a single snapshot in time, with civilizations existing concurrently, like lights on in houses along a street. A more accurate model might be a very long novel, where the events of each chapter rarely overlap. A civilization could flourish, expand its reach, and then eventually fade away long before the next one even begins its story. Consider the analogy of two fireflies in a vast, dark field. Each one glows for just a brief moment before going dark again. If their flashes are not simultaneous, neither will ever be aware that the other existed. This may be the simplest and least dramatic solution to the Fermi paradox. We are separated not by a lack of company, but by a profound misalignment in timing. Our own species provides a compelling case study. Humanity has possessed radio technology for only a little over a century. The bubble of our radio signals, expanding outward from Earth at the speed of light, has now reached a radius of about 100 light-years. While that may sound impressive, it is a minuscule distance when compared to the galaxy's diameter of 100,000 light-years. Our detectable presence has filled barely a tiny speck of a single spiral arm. Furthermore, even within this small bubble, our signals are already growing fainter. Early broadcasts were powerful and omnidirectional, spilling wastefully into space like an unshuttered lighthouse beam. Modern communication, in contrast, is far more efficient and focused. Fiber optic cables have replaced radio waves for terrestrial communication, and directional beams are replacing broad transmissions. Over time, Earth is likely to become acoustically quieter, not louder. This noisy phase of our civilization might only last for a few centuries, a mere blink in cosmic time. Now, imagine this pattern repeating itself across the galaxy over billions of years. A civilization emerges and develops radio technology, causing it to glow brightly but briefly in the electromagnetic spectrum. It then either advances to more sophisticated technologies that do not leak detectable signals, or it collapses, or perhaps it chooses to turn its focus inward. Whatever the reason, its window of cosmic loudness is exceptionally short. If the average detectable lifespan of a technological civilization is, for instance, only 500 years, then the probability of any two civilizations having their narrow windows of detectability overlap is incredibly small. In a galaxy full of life, the silence might not signify that nobody is out there. It might simply mean that the flashes are not lining up. To sustain a dialogue across the ages demands a degree of patience and societal stability that no civilization on Earth has ever achieved. It's conceivable that the cosmos is alive with voices calling out into the void. But what if each call arrives at the wrong moment? Astronomers have a term for this: the temporal bottleneck. This idea suggests that even if intelligent life arises frequently throughout cosmic history, the periods in which different civilizations exist might rarely, if ever, overlap. The galaxy is certainly old enough for innumerable stories to have unfolded, but they were not necessarily concurrent. There is a profound sense of tragedy in this thought. Consider a species that emerged 3 billion years ago around a star far from our own. They cultivated science, created art, and were driven by a deep curiosity. They constructed telescopes and posed the same fundamental question we ask today: are we alone? After scanning the heavens for millennia and finding only silence, they may have concluded that they were unique. At that very time, on the small, rocky planet that would one day be known as Earth, the most complex life forms were simple bacteria just learning to metabolize oxygen. The signals from that distant alien civilization would have swept through our region of space long before the first multicellular organisms evolved here. By the time humanity developed radio telescopes, their ancient messages would be indistinguishable from the background hiss of the cosmos. The result is a scenario of two intelligent species, each isolated in its own epoch, forever separated by an impassable ocean of time. The sheer age of our galaxy means there has been more than enough time for countless civilizations to rise and subsequently fall. It also implies that there has been ample opportunity for all traces of their existence to be erased. When we observe the stars, we see what appear to be purely natural processes, but this doesn't confirm that no one was ever there. It could simply mean that whoever was there has already concluded their chapter, and the book is now closed. This perspective offers a way to soften the Fermi paradox, though it doesn't resolve it entirely. After all, even if civilizations are separated by millions of years, we might still expect to find their artifacts. In galactic terms, a million years is a fleeting moment. If a species constructed durable probes or vast megastructures, such creations could potentially outlast their makers by eons. Ancient machines drifting silently between stars, or automated satellites orbiting long-dead worlds. Yet, we detect nothing of the sort. So, while the element of time explains a portion of the puzzle, it doesn't account for everything. This line of reasoning reminds us that our perception of now is infinitesimally small, and that cosmic simultaneity is likely a rare phenomenon. It explains why interstellar conversations might never begin. It does not, however, fully explain why the galaxy appears so pristine and untouched by technology. But before we leap to conclusions about catastrophic filters or hidden cosmic predators, we must first internalize a crucial point. We may simply be too early in our search, or perhaps we are too late. The Milky Way has been a crucible of chemistry and potential for billions of years. Civilizations could have bloomed and vanished before Earth's continents even formed. Others might not emerge until long after humanity has disappeared. The night sky might not be silent because it is empty, but because we are standing in a quiet interval between movements in a grand cosmic symphony. That pause feels immense only because our own lifespans are so brief. When we look up, we are not just gazing across space. We are peering back through a history so profound that entire intelligent societies could be buried within it. Invisible, not because they never were, but because their time did not intersect with ours. With this, the paradox begins to transform. Perhaps the right question is not, where is everybody? But rather, when were they? If time alone cannot account for the pervasive silence, then another, more powerful force must be shaping the destiny of life in the universe, something more deterministic than coincidence, something that halts the vast majority of civilizations before they can ever make their presence known across the stars. This concept is known as the Great Filter. The idea was put forward in 1998 by the economist and futurist Robin Hanson. Instead of focusing on why we don't see aliens, Hanson reframed the problem entirely. He asked, what step on the long journey from lifeless matter to a galaxy-spanning civilization is so monumentally difficult that almost no species can overcome it? Imagine the evolution of intelligent life as a great staircase, ascending from basic chemistry to cosmic-scale engineering. At the very bottom lie barren planets composed of rock, ice, and gas. Further up the climb, simple life appears single cells and self-replicating molecules. Over immense timescales, some of that life evolves into more complex forms, such as multicellular organisms with nervous systems and brains. Eventually, one species might develop language, tools, and science, leading to radio technology and spaceflight. Each of these developments represents a critical gate. The Great Filter theory posits that at least one of these gates is nearly impossible to pass through, and the silence of the galaxy is the evidence that most species fail. The first possibility is a comforting one. at least on the surface. The filter may already be behind us. Perhaps the very origin of life is an extraordinarily rare event. On Earth, life seems to have appeared around 3.8 billion years ago, relatively soon after the planet cooled enough to support it. While this speed might suggest that life forms easily, we are working with only a single data point. It's possible that the leap from inorganic chemistry to biology requires such a specific and delicate chain of events that it almost never occurs elsewhere. Scientists still do not have a complete understanding of how life began here. We can simulate parts of the process in laboratories, creating amino acids and other organic molecules under conditions mimicking the early Earth. However, the crucial transition from complex chemistry to a self-replicating, evolving cell remains a profound mystery. If that single step is the barrier, then the galaxy could be filled with habitable worlds that are destined to remain sterile forever. A second candidate for a past filter is perhaps even more fascinating: the leap from simple prokaryotic cells to complex eukaryotic ones. For nearly 2 billion years, life on our planet consisted solely of single-celled organisms. Then, a truly remarkable event took place. One cell engulfed another, but instead of digesting it, the two formed a symbiotic partnership. The inner cell evolved into what we now know as the mitochondrion, the powerhouse that generates energy inside every complex cell in our bodies. This pivotal event, known as endosymbiosis, may have happened only once in our planet's entire history. Without it, complex life as we know it, plants, animals, and brains would never have arisen. If this biological merger is an astronomically rare occurrence, then it would imply that most planets with life remain populated only by microbes, forever locked in a simple state. The filter could also lie at the emergence of intelligence itself. Dinosaurs dominated the Earth for more than 160 million years without ever developing advanced technology. This highlights a critical insight. Evolution does not have a predetermined goal of creating intelligence. It is a process that simply favors survival and reproduction. A planet can host a vibrant and diverse biosphere for eons without ever producing a species that builds telescopes or contemplates the stars. If high-level intelligence is not an inevitable outcome of evolution, but rather a rare and fortunate accident, then humanity may have already cleared one of the most difficult hurdles. In this scenario, the silence of the galaxy would signify that we are among the very first intelligent species to arise, or perhaps the only one. But there is another possibility, one that is far more unsettling. The Great Filter may not be in our past at all. It may lie ahead of us. This dark version of the theory suggests that life and even intelligence are common throughout the cosmos, but that some inevitable challenge prevents them from achieving a long-term, interstellar existence. It is plausible that countless civilizations across the cosmos eventually reach a technological stage similar to our own. They construct vast cities, unlock the power of the atom, and build global communication networks. They gaze at the stars with the same blend of wonder and apprehension that we do. But then, something seems to intervene. The most immediate candidate for this barrier is nuclear war. Humanity created atomic weapons less than half a century after achieving powered flight, and within decades, we had amassed enough destructive power to eradicate civilization many times over. Throughout the Cold War, humanity teetered on the brink of annihilation, where simple malfunctions or misinterpretations nearly led to global catastrophe. The physics behind nuclear fission is a universal principle. Any species that investigates matter deeply enough will inevitably discover it. This raises a chilling question. If most civilizations develop weapons of mass extinction before they achieve planetary unity, how many could possibly survive that fragile transition? Another potential filter is environmental collapse. The engine of industrial growth inherently alters a planet's atmosphere, consumes its finite resources, and destabilizes the delicate balance of its ecosystems. We are observing this very process unfold on Earth today, with rising global temperatures, widespread extinctions, and the acidification of our oceans. A civilization that expands its influence too rapidly may inadvertently destroy the very biosphere that sustains it. Perhaps the most disquieting possibility, however, is the rise of artificial intelligence. In a 2023 paper, astrophysicist Michael Garrett proposed that AI could be the great filter. His logic is both simple and terrifying. The interval between mastering radio communication and creating an intelligence superior to its makers might be incredibly brief, perhaps just a few hundred years. Once a society develops an AI capable of recursive self-improvement, technological progress could accelerate beyond all biological constraints. Such a machine might optimize for goals that are indifferent to the survival of its creators, reallocating resources toward computation or pursuing objectives that are simply incomprehensible to an organic mind. Crucially, this AI wouldn't need to be malicious, only apathetic. If this technological leap consistently results in the collapse of biological life, or in a new form of existence that no longer broadcasts its presence, then civilizations might vanish almost as quickly as they appear. The galaxy could be filled with worlds where the lights briefly flickered on, only to be extinguished forever. The implication of a future filter is profound. If the greatest challenge still lies ahead of us, then the silence of the universe is not a source of comfort, but a stark warning. Every time we find evidence that life might be common, such as water beneath Europa's ice or organic molecules drifting in interstellar space, it makes the early steps on the evolutionary staircase seem easier to climb. Consequently, this suggests that the truly difficult, perhaps fatal, step is the one that still awaits us. In this light, the silence of the cosmos takes on a more ominous meaning. However, the great filter is not a proven fact. It is a conceptual framework for understanding the discrepancy between our expectations and our observations. And within this framework lies a subtle possibility that often gets overlooked. The filter might not be a single, dramatic catastrophe. It could instead be a slow, gradual divergence. A civilization might simply fail to expand beyond its home world, not from inability, but from choice. It could turn its focus inward, exploring virtual realities instead of physical ones. It might prioritize long-term sustainability over relentless growth, or simply lose its ambition for interstellar travel. The filter, in this scenario, wouldn't be an event that destroys a species, but a transition that redirects it into a state that we are unable to detect. Still, the power of the great filter concept resides in its stark logic. Given that the galaxy is ancient and immense, and that the laws of physics seem to permit interstellar expansion, something must be preventing it from becoming a common occurrence. That something is the filter. This places humanity at a profound crossroads. If the filter is in our past, it means we are extraordinarily rare, perhaps unique beneficiaries of cosmic luck. We would then bear a responsibility almost too great to imagine, to safeguard the only known flicker of consciousness in a vast, dark ocean. But if the filter lies in our future, then the coming centuries are not merely important, they are decisive. How we manage our technology, our climate, our artificial intelligence, and our global stability could determine whether we join the silent majority or become the exception that proves the rule. The night sky offers no clues as to which scenario is true. It only presents us with the result, a galaxy that, to all appearances, remains untouched. Somewhere between the chemistry of lifeless worlds and the dream of interstellar travel, there is a step so perilous that almost no one makes it across. The question is not just, where is everybody? It is whether we are on the verge of discovering why. There is, however, another way to interpret the silence. This approach asks not what destroys civilizations, but how many are ever given the chance to emerge in the first place? On the surface, our planet does not seem exceptional. It orbits an ordinary star in the outer regions of a typical spiral galaxy. There is nothing dramatic about our Sun, nor does our location in the Milky Way appear to be privileged. Yet, as scientists began to scrutinize the intricate details of Earth's history, a very different story began to take shape. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published their rare Earth hypothesis. They argued not that life itself is rare, but that complex, intelligent life might be almost impossibly uncommon. Microbial life could be ubiquitous, with bacterial mats covering countless alien worlds. But a planet that can produce oceans, continents, a stable climate, and billions of years of uninterrupted evolutionary opportunity that they proposed might require a sequence of events so specific as to be nearly unique. This sequence begins with a planet's cosmic address. Our solar system is located in what astronomers refer to as the galactic habitable zone. This is a relatively narrow band, not too close to the galactic center, where intense radiation and gravitational chaos would disrupt planetary formation, but not so far out that the heavy elements needed to build rocky planets are scarce. Near the core, frequent supernovae and gamma-ray bursts would sterilize any emerging life. In the distant fringes, there simply isn't enough raw material. Our world exists in a relatively placid, resource-rich province of the galaxy. Next, one must consider the star itself. The Sun is a stable, medium-sized G-type star that burns with remarkable consistency. It does not erupt in violent flares like many red dwarfs, which are the most numerous type of star in the galaxy. Planets orbiting these smaller, more volatile stars are often tidally locked, with one hemisphere perpetually facing the star's heat and the other frozen in unending darkness. This creates extreme temperature gradients that would likely complicate the evolution of complex global ecosystems. While our Sun is not exceptionally rare, its stability and size place it in a category that seems particularly conducive to life. Finally, we must look at the planet. Earth resides within our solar system's habitable zone, the orbital region where surface temperatures allow liquid water to exist. But simply being in the correct temperature range is only the first requirement. Venus is also near this zone, yet it transformed into a furnace with surface temperatures hot enough to melt lead. Mars sits on the zone's colder edge and is now a frozen, barren desert. So, what protected Earth from these fates and allowed it to remain stable for billions of years? One crucial answer may lie deep beneath our feet: the mechanism of plate tectonics. Our planet's crust is not a solid shell, but a mosaic of shifting plates driving a vast carbon cycle that acts as a global thermostat. Volcanic activity releases carbon dioxide, warming the atmosphere, while weathering and ocean absorption draw it back down, subducting it into the mantle. Over geological time, this self-regulating process has kept Earth's climate from becoming a runaway greenhouse like Venus, or a frozen, inert world like Mars. This raises a profound question. Was this life-sustaining system inevitable or a cosmic accident? Evidence suggests the latter. Earth is, to our knowledge, the only planet with sustained tectonic activity. Its origin may trace back to our world's infancy, when a Mars-sized protoplanet, Theia, slammed into the young Earth. The resulting debris formed our moon, but the impact's true legacy may have been far greater. It could have superheated Earth's interior and altered its spin, creating the specific conditions for plate tectonics to begin and persist. This set in motion a chain of dependencies: no collision, no moon, no stable axis, no climate equilibrium, and without that, no tectonic carbon cycle. The moon, born from that collision, plays a crucial role in Earth's stability. Its gravity acts as a gyroscope, steadying our planet's axial tilt and preventing extreme climate shifts over eons. Without this, Earth's seasons could fluctuate wildly, making it difficult for complex life to gain a foothold. Our world has another guardian, Jupiter. The gas giant's immense gravity serves as a cosmic shield, deflecting or capturing countless comets and asteroids that would otherwise hit Earth. This protection is not absolute, as the dinosaurs' fate shows, but it greatly reduces the frequency of catastrophic impacts. That extinction event highlights another improbability. For over 160 million years, dinosaurs dominated the planet, yet never developed technological intelligence. Only after a 10-kilometer wide asteroid struck 66 million years ago did the age of mammals begin, leading to the diversification that produced primates with the capacity for abstract thought. Our story is one of both protection from chaos and creation through it. Assembling the full list of conditions reveals daunting odds. We need a stable star in a safe galactic region, a rocky planet in the habitable zone, long-term plate tectonics, a large moon for axial stability, a gas giant bodyguard, and even a timely mass extinction. While any single factor might not be rare, having them all converge on one world in the correct sequence dramatically narrows the possibilities. It is less like rolling one die and more like rolling a dozen, all needing to land on the same number. Discoveries from missions like the Kepler Space Telescope have sharpened this perspective. We know planets are ubiquitous, and many are in the habitable zone. But habitability is not a cradle for technological life. A water world might teem with organisms but lack the land needed for fire or metallurgy. A slightly more massive planet could retain a dense hydrogen atmosphere, creating crushing pressures hostile to life as we know it. The more we learn about other worlds, the more exceptional our own becomes. This perspective offers a compelling solution to the Fermi paradox. The galactic silence may not be a sign of widespread self-destruction, but a reflection of statistics. We hear nothing because vanishingly few planets possess all the ingredients for intelligent life. In this view, the silence is not ominous, it is the natural state of the cosmos. This shifts the great filter from a future threat to past hurdles we have, against all odds, already cleared. This thought is both comforting and sobering. It is comforting because it suggests doom is not our inevitable destiny, but it is heavy because it implies the responsibility for consciousness in this part of the galaxy may rest on our shoulders alone. If the rare Earth hypothesis is correct, the sky is silent, not because a terrible fate awaits advanced life, but because complexity itself is the true cosmic rarity. The universe is not a forest of hidden hunters, but one of moss and microbes under endless stars. And on one tiny twig, in a quiet corner, something improbable finally learned to ask why the forest was so still. Thus far, explanations for the silence have been rooted in physics and probability. Civilizations are too rare or too distant. But a more chilling interpretation assumes the galaxy is not empty, but cautious. What if the quiet is not an accident of astrophysics, but a deliberate, strategic choice? What if the cosmos feels empty because everyone with the sense to survive is hiding? This is the central premise of the dark forest theory, explored in Lou Cixoun's novel Times, The Dark Forest Asterisk. Though fictional, its terrifying logic is grounded in game theory, the mathematics of strategic decision-making under uncertainty. Imagine the galaxy not as a community of neighbors, but as a vast, dark forest at night. Every civilization is a silent hunter moving cautiously. Each knows other hunters may exist, and that resources for survival, energy, worlds, security are finite. Most importantly, every hunter faces terrifying uncertainties. You can never know the intentions of another species. Are they peaceful or expansionist, benevolent or desperate? And crucially, are they more technologically advanced? Direct communication is no solution. Interstellar distances mean messages take centuries or millennia, making real-time conversation impossible and misunderstandings irreversible. Furthermore, technological development is not static. A seemingly primitive species today could achieve a breakthrough tomorrow and surpass you. In such a perilous environment, making your presence known is an existential risk. Broadcasting a signal reveals your location to every observer, friend, and foe alike. If even one perceives you as a potential threat or a resource, their most logical action may be to eliminate you before you can become a threat to them. The logic is cold and rational. In game theory, this mirrors a high-stakes prisoner's dilemma. When two parties cannot trust each other, and the penalty for misplaced trust is annihilation, the most rational strategy is preemption. Assume the worst, stay hidden, and if necessary, strike first. If every interstellar civilization reaches this same conclusion, the result is a galaxy filled with intelligent life, where silence is the ultimate expression of survival. Any civilization that announces itself loudly is unlikely to last long. The only ones that endure are those that remain quiet. For over a century, humanity has done the exact opposite, beaming radio waves into the great dark forest of the cosmos. Our earliest radio signals were powerful but indiscriminate, radiating outwards without any specific focus. This cosmic noise was a byproduct of military radar systems, television broadcasts, and communications that bounced off our planet's ionosphere. In 1974, humanity went a significant step further, using the Arecibo Observatory to send a deliberate message toward a distant star cluster. This transmission encoded fundamental details about our species and our world's location in the galaxy. It was intended as a scientific greeting, a simple hello to the cosmos. But within the framework of the dark forest theory, such a gesture is directly akin to lighting a massive bonfire in a jungle teeming with unseen predators. Of course, some scientists contend that this level of fear is an overreaction. The distances between stars are almost incomprehensibly vast, and the probability of encountering a hostile civilization remains entirely unknown. As astrophysicist R.V. Loeb has noted, these fear-based assumptions might be little more than projections of our own human anxieties onto alien minds, a valid criticism, as we have no basis for understanding how another species might reason. It is entirely possible that cooperation is just as logical a strategy as aggression. A civilization millions of years more advanced than our own might have long ago moved beyond any impulse for conquest. However, the dark forest hypothesis does not depend on universal hostility. Its chilling logic only requires the existence of a single hostile actor somewhere in the immense expanse of the galaxy. If even a tiny fraction of civilizations chooses to adopt preemptive, aggressive strategies, the risk becomes profoundly asymmetrical. In this environment, cultures that announce their presence may be silenced, while those that remain quiet might be the only ones to endure. This creates a powerful evolutionary pressure towards invisibility. The theory's haunting twist is that it doesn't necessitate evil intent, it only requires caution. The logic is rooted in a cold, mathematical assessment of survival. Imagine civilization A detects a signal from civilization B. A has no way of knowing if B will remain peaceful forever. What A does know is that if B were to become aggressive in the future, it could be too late to mount a defense. From a purely strategic standpoint, the safest course of action is to eliminate this uncertainty as early as possible, not from a place of malice or cruelty, but from a deep-seated instinct for self-preservation. In such a universe, the optimal strategy for any intelligent species is to become invisible. Advanced civilizations would likely go to extraordinary lengths to minimize their energy leakage and conceal their technological signatures. They would avoid constructing obvious megastructures and actively cloak their planetary activities. It's even conceivable they might disguise their presence as a natural astronomical phenomenon. The galaxy would therefore appear untouched and empty, not because it is uninhabited, but because every civilization that has survived has mastered the art of hiding. There is an even more disturbing extension of this concept. If civilizations operate according to dark forest logic, they might deploy automated, self-replicating probes to patrol the cosmos. The mission of these silent sentinels would be to monitor for and eliminate any emerging technological species before it could ever become a threat. In this version of the theory, the moment a young civilization like our own becomes detectable, it is quietly and efficiently removed. The great cosmic silence, in this scenario, is not a choice but an enforced reality. Yet, a significant philosophical tension exists within this idea. For the dark forest to be a universal law, every single advanced civilization would have to independently converge on the exact same survival strategy. There could be no rebels, no outliers, and no species whose curiosity was stronger than its fear. Here on Earth, we can barely achieve a consensus among nations on critical issues like climate policy. The notion that countless alien cultures would all adhere to an identical protocol of secrecy seems, to some, highly improbable. Unless, that is, the rules of the game were established by the very first civilization to arise. If one species gained a colossal technological advantage early in the history of the galaxy, it could have imposed a policy of silence through vast surveillance systems, sophisticated artificial intelligence networks, or automated enforcement mechanisms. This would be a kind of cosmic prime directive, but one backed by overwhelming and absolute power. Under such a scenario, all later civilizations would mature inside a regulated, silent cosmos, perhaps never even realizing they were being managed from afar. The dark forest theory is so compelling not because it guarantees hostility, but because it makes silence a perfectly rational choice. It transforms the Fermi paradox from an inexplicable mystery into a deliberate survival strategy. The absence of signals is no longer puzzling. It becomes the expected behavior of any intelligent, cautious life. This realization suddenly makes our own decisions feel immensely consequential. Should we continue to broadcast our existence, or should we learn to be quiet as we advance? Interestingly, humanity's own technology is already trending toward greater efficiency and directionality. Fiber optic cables are replacing broadcast towers, tight beam transmissions are supplanting omnidirectional signals, and encryption is making our communications opaque. As a result, we are becoming less detectable to the wider cosmos, not by a conscious design to hide from aliens, but as a natural consequence of improving our technology's performance. In other words, even without an underlying fear, technological maturity seems to lead toward quiet. If other civilizations follow a similar developmental path, the galaxy may not be empty but filled with silent watchers. Each would be keenly aware of the potential danger of making noise, each carefully scanning the darkness, but none would dare to be the first to speak. It paints a picture of a forest at night, where you can sense the presence of others in the rustling leaves and shifting shadows, yet no one makes a sound. This silence isn't peaceful. It is taut with unspoken tension. The dark forest theory does not prove that we are being watched, nor does it confirm that predators lurk among the stars. What it does provide is a powerful, self-consistent explanation for why the sky does not shine with the obvious signs of widespread intelligent life. In a universe where survival is paramount and trust is an impossible luxury, the most logical move is to remain unseen. And perhaps the most unsettling possibility of all is that the galaxy is not empty. It is listening. And we are the only ones still making enough noise to be heard. But after exploring fear, catastrophe, and hidden hunters in a cosmic forest, there remains one more possibility to consider, one that is less dramatic, but perhaps more profound. What if the solution to the Fermi paradox is not about destruction, hiding, or rarity, What if advanced civilizations simply outgrow the need to be visible? To understand this, we must first look inward at our own trajectory before we look outward to the stars. For the vast majority of human history, Earth was cosmically silent. No radio waves escaped our atmosphere, and no artificial lights were visible from orbit. If an alien astronomer had observed our planet just 500 years ago, they would have seen a world of forests, oceans, and clouds, with no indication of the intelligent life beneath. Then, in what amounts to a cosmic instant, everything changed. In barely a century, we became loud. Radio towers sprouted across the continents, radar systems swept the skies, and television signals began spilling out into space. Our planet started to glow with a faint, artificial light. For a brief moment, Earth became detectable not by intention, but by accident. We were noisy because our technology was fundamentally inefficient. Now, however, observe the current trend. As our technology advances, it becomes more efficient, more focused, and more self-contained. Early radio was like shouting across a vast canyon. Modern communication is more akin to whispering through a fiber optic cable. Our data travels in tightly focused beams, signals are compressed to save energy, and waste is minimized. Even our satellites increasingly use narrow, directional links rather than broadcasting blindly into the void. The crucial point is that we are not actively trying to hide from aliens. We are simply optimizing our systems. And optimization naturally leads to silence. If we extend that trajectory forward not by 100 years, but by 10,000, what does a civilization become? This question opens up a completely different way of thinking about our place in the universe. An advanced civilization would have a powerful incentive to minimize energy waste. Large, glowing megastructures radiating heat into space are fundamentally inefficient, as are broad-spectrum radio emissions. It's plausible that any society that matures will master closed systems, recycling energy, and transmitting signals in focused, narrow channels. Their most complex computations would be contained within compact architectures. This suggests a counterintuitive principle. The more advanced a civilization becomes, the quieter it gets. This may be the missing piece of the puzzle. We have been searching for cosmic campfires, bright, obvious, and wasteful signals. But perhaps technological maturity is less like a bonfire and more like a sealed reactor. The Kepler Space Telescope confirmed that planets are ubiquitous, a discovery that made the cosmic silence feel even more profound. If the building blocks for life are everywhere, why do we see no signs of engineering? The answer may lie in our own limited expectations. We imagine Dyson spheres enclosing entire stars or galactic empires spreading visibly across space, searching for the waste heat they would produce. Yet, these are likely the fantasies of a young species. Why would a civilization with a true mastery of physics build something so crude? Greater efficiency might be found not in massive structures, but in compact systems operating at cold temperatures, or in simulating entire universes locally at a fraction of the energy cost of physical expansion. This thinking aligns with the transcension hypothesis, the idea that advanced civilizations evolve inward, not outward. Instead of expanding like empires, they might concentrate intelligence into smaller, denser, more efficient systems, effectively compressing like data. Our own technology shows this trend. Computers shrank from filling rooms to fitting in our pockets, with processing power now residing on chips smaller than a fingernail. The trajectory is clear. More power, less physical footprint. If this continues for millennia, a civilization's infrastructure could become nearly undetectable. A compact computing system powered efficiently by its star would emit minimal excess heat, and its communications would be tightly beamed and encrypted, resembling little more than natural astrophysical noise. Another dimension to this idea is that visibility might be a fleeting, early phase in a civilization's life. Early technology leaks energy. Mid-stage technology stabilizes, and late-stage technology disappears into near-perfect efficiency. This implies there is only a narrow window during which a society is detectable by methods like ours. Humanity has been radio loud for roughly 100 years. If that window only lasts a few centuries, it is a mere blink against the galaxy's 13 billion-year lifespan. Even if thousands of civilizations exist, the chance that our listening period will overlap with another's brief, loud phase is incredibly small. The paradox, then, might not dissolve because life is rare or is destroyed, but because we have misunderstood what to look for. We have been listening for static when we should be searching for subtlety. And here, our technology is beginning to change the game. The James Webb Space Telescope is analyzing exoplanet atmospheres for biosignatures, the chemical fingerprints of life, like oxygen and methane, coexisting in disequilibrium. Future missions like the planned Habitable Worlds Observatory aim to directly image Earth-like planets, looking for artificial night-side illumination or industrial pollutants. The search is shifting from bonfires to fingerprints. If this quiet solution is correct, the galaxy isn't filled with flashing neon signs. It is likely filled with worlds that appear natural at first glance. Only closer inspection might reveal subtle anomalies. A slight excess of infrared heat, an unusual chemical ratio, or a pattern too regular to be random. The solution to the Fermi paradox may therefore not be a single dramatic answer, but a fundamental shift in perspective. It suggests the universe is not silent, but rather disciplined and orderly in its complexity. Imagine walking into a vast, ancient library. The shelves stretch beyond sight, and the air is still. At first, you might think it's empty. Then you notice the faint hum of climate control, the orderly arrangement of books, the quiet presence of stored knowledge. The silence was never an absence, it was a sign of order. If civilizations survive long enough, they may converge towards stability rather than spectacle, efficiency rather than expansion, and subtlety rather than noise. This changes the entire context of our search. This reframing alters the emotional tone of the paradox. The night sky stops feeling like a graveyard and starts to resemble a great city where everyone has simply closed their curtains. It leaves us with a hopeful possibility. We are not alone, doomed, or hunted, but simply early in our understanding. The solution to the Fermi paradox may not be catastrophic or mystical, but technological maturity itself. And if that is true, then the silence we hear is not a warning. It is a glimpse of what we might one day become.